Today we're covering material in preparation for section 4.5, and what we're going to be looking at is all of our different techniques for factoring. We have learned several throughout this course, so I wanted to sum it all up here, get some really good practice in, and you'll see with these practice problems later on that it's all mixed up, all the different techniques that you need to learn and get used to using. And so here you can practice how different techniques come up and how you want to approach different problems different ways. So without further ado, let's go through one of each of these problem types, and then I highly recommend that you give these practice, especially with the upcoming test. So the first factoring technique that we learned was this first one that says we need to factor out the greatest common factor. And so that's when we look at something like 6x cubed plus 9x squared, and we pull out their highest common factor. So between 6 and 9, the largest common factor there is going to be a 3. And then between x cubed and x squared, well, the largest factor that we can pull out there is an x squared. And so when we factor that to the front, we got to think about what we're left with. Well, if I pull a 3x squared out of a 6x cubed, then I'm going to have 2x left over, because the 3 and the 2 multiply to make the 6, and x squared times x makes x cubed. Now if I look at 9x squared and I pull out 3x squared, I'm left with just plus 3. The x's are gone. I've pulled all of x squared to the front, and 9 divided by 3 leaves us with 3. So that's the fully factored form here. The next one is a trinomial, which we typically break up into our sets of parentheses like this, and we draw our x's in the first position. This is the easier example because our leading coefficient here is 1. There's no number in front of the x squared, and we always want to think about what multiplies to 12 and adds to 4. Well, if we think about factors of 12, we could have 1 and 12. We could have 2 and 6. We have 3 and 4. But I can't use 3 and 4 anyway to add together to make a 4. But with 2 and 6, I could get those to add or subtract to 4. So I'm going to go with 2 and 6. Now is when we think about our signs. Now we know that we need to multiply to a negative 12. So we know that they need to have opposite signs, because if I had a negative times a negative, it would give me a plus 12. Here we have a minus 12, so we know they're opposite signs. And I know that the minus is going to go with the bigger number, the 6, because we got a minus 4 in the middle. And that means I have x plus 2 on the other side. So that's our super standard way of factoring quadratics when we think about what multiplies to 12 and adds to 4. Now for the trickier version of factoring trinomials, we're still doing this method of breaking it into these two sets of parentheses, only now we have a 2 in front of our x squared term. So we must have a 2x and an x that multiply in our first positions to make that 2x squared. So now we have to think through combinations of what multiply to 3. I could have a 3 and a 1, or a 3 and a 1 like that. So we have options, and we have to think about, well, how can I make a 5 in the middle there? Well, if I look at my outer and my inner here, basically what makes up that middle term when we FOIL things out, I would have a 3 times an x here and a 2 times x here, and that would be 3x plus 2x, which does give us a 5x, which is great. Now, just for comparison, if we had gone with a 2x and a 1 and an x and a 3, we would have been looking at, with the middle ones, we would have had an x, and here we would have had a 6x, but x plus 6x gives us 7x, and that's not what we were looking for, okay? So with these, the tricky thing about it when they have these leading coefficients is that you have more combinations to test, basically. But as long as you go through them and think about how do I make that middle term, you can figure it out. So here we end with a plus 3, which means that they're matching in sign. And since we have a plus 5x, I know both of those signs are positive. So it's 2x plus 3 and x plus 1. And of course, I could always multiply out, FOIL out what I've just factored in order to check that I got the right answer. Now we're going to look at difference of squares. So this is a special case with quadratics that are typically a little bit easier to solve. Anytime when you have a square, which is typically x squared in the first position, minus some b squared, then you can always break it out into this a minus b, a plus b business. Basically, the middle terms disappear when we have the alternating signs like that. So if we use that as a rule on x squared minus 16, that would break into x minus 4 and x plus 4. Here my b value is 4, since 4 squared makes 16. Now, similarly, we can apply this rule to numbers that are not naturally squares, like 5. And all we do is put a square root on the number. So this would be x minus root 5 and x plus root 5. So we can apply our difference of squares rules on non-squares. We just throw a square root in there and it makes it work. It makes it really easy to factor and find your roots that way typically. So there's all of those techniques. Those are 4 of them so far. Now we're going to look into some higher degree polynomials. Some of these techniques we've learned as well. This next one is factoring the cubic by grouping. And with this one is where we look for what's common between our first 2 terms. Well, between the first 2 terms, x cubed and 3x squared, I can pull out an x squared. I'm left with x plus 3 then. And I haven't done anything to the next 2 terms. Well, if I could get an x plus 3 again out of that second 2 terms, that would be really great. And the way to make that happen is to factor out this minus 4 that's sitting in front of the x. When we do that, we have x squared times x plus 3. That doesn't change. Minus 4, parentheses. Then, of course, the minus 4x, when we pull out the minus 4, is just x. When we look at the minus 12 and we pull out a minus 4, we're left with a plus 3. And there we have a repeated x plus 3 term, which is really great because now we can pull that x plus 3 term to the very front. And we have x plus 3. And with this first term, I'm left with x squared. And on the second term, I'm left with a minus 4. Which, of course, using our square minus the square rule, or difference of squares rule, we can factor that one more step. X plus 3 doesn't change. This becomes x plus 2, x minus 2. And there's our fully factored version. So typically with cubics, we use one technique in order to break it down so we get to a quadratic, and then we use some other technique to break down that quadratic. Now for our last standard technique here, we want to think about u substitution. So for this example, we're looking at x to the 4 minus 8x squared plus 15. And that's very similar to something we're used to factoring, only it's an x to the 4 term and an x squared term. But if instead it had been something like u squared minus 8u plus 15, we would immediately know how to factor that. And when we do that kind of step, when we look at that polynomial instead, that's what we call u substitution, where we're taking u to be x squared. Well, when we do that, and we look at the u squared minus 8u plus 15, we can easily think, well, what multiplies to 15 and adds to negative 8? Naturally, 3 and 5 multiply to 18, and they also add to 8. So this becomes a pretty easy factoring problem. We're going to have a 3 and a 5. Again, those multiply to 15, and they add to 8. Notice the 15 is positive, which means they must match in sign. I'm either had a negative times a negative or a positive times a positive. And since I actually have a minus 8u, I know that they're both negative, and they both then add to a negative 8. So that is our factoring with u in it. Only the question didn't actually ask for with the answer with u's in it. It, of course, wants something with x's in it. So we can stick our x squared back in. We know u equals x squared, and so when we plug that back in, it looks like this. And now we can really apply our difference of squares rule one more time, and we get x minus root 5, x plus root 5, x minus root 3, x plus root 3. So there, you can see we took this quartic, this degree 4 polynomial we normally could not have factored. We were able to factor it all the way down to its linear factors, just using this quick substitution rule and our standard methods for factoring. So I highly encourage you to give that practice. Those 6 techniques, 6, shows up in all of these 40 different problems in various different orders, and so it really makes you have to think and look for certain things to know how to factor different ways. So as always, if you have any questions, please reach out and check the answer key as well. Let me know if you have any questions. Thank you so much.